Today, we are going to analyze the relation between the product of two matrices and the operation of transposing matrices. If you forgot how to multiply matrices or how the transpose of a matrix works, you may need to take a look at our previous videos. You will find the links in the description below. Let's get straight to the point. We take a matrix A with m rows and n columns. This is what actually the capital pink M means. Then a matrix B with n rows and their columns, so that the product A times B exists, because the number of columns of A coincides with the number of rows of B. Don't forget that the matrix A times B has m rows and r columns. Putting these tedious notations aside, we simply want to know if the transpose of the product A times B is the same as the transpose of A times the transpose of B. Before I give you an answer, I'd like you to take some time to think about it. You can even stop the video if you need more time, and then you can come back to check if your answer was correct. Well, I am sure we all agree that the answer is no. It is actually very easy to find examples where this property is not satisfied. For instance, we can consider this one. Our first matrix A is a 2 times 2 matrix, and our second matrix B is a 2 times 3 matrix. We first compute the transpose of the product of A and B. So first we need the product of A times B, which is given by the matrix 1, 0, 3, minus 2, 1, 6. Let's just check a couple of entries together. For example, we can consider the first row of A and the first column of B. Then we compute 1 times 1 plus 0 times minus 4, and we obtain 1, which is the one here. Then we can, for instance, consider the second row of A and the third column of B, and we obtain 2 times 3 plus 1 times 0, which is equal to 6, which is the 6 that we have here in the last position. Then, in order to obtain the transpose, we simply need to invert rows and columns, as we know. Now we come to the second step. Let's multiply the transpose of A with the transpose of B in this precise order. Remember that the product is not commutative. Check the link in the description below if you need more details. Then, surprise, surprise, we observe that the first matrix is a 2 times 2 matrix, while the second matrix is a 3 times 2 matrix. Unfortunately, the number of columns of the first matrix is different from the number of rows of the second matrix. So we cannot compute this product. We cannot multiply those two matrices. This example shows that our first question has a negative answer. So is it really worth looking for a relation between the product and the transpose? The answer is yes this time, because actually we know that the transpose of A times B is equal to the transpose of B times the transpose of A. Again, in this precise order, which is the opposite of what we wrote before. So let's take the previous example. We have our matrices A and B and the transpose of the product that we already checked. We simply need to compute BT times AT. Now the multiplication makes sense because the number of columns of BT then coincides with the number of rows of AT. Let's check one entry of this product just for fun. So here we can consider, for example, the second row of the first matrix and the second column of the second matrix. This gives rise to the following computation, which is 0 times 2 plus 1 times 1 which is equal to 1. Then what we obtain is exactly the matrix transpose of the product AB. So at least for this example, the property holds. I am sure that many of you would like to know the simple proof of this nice result. So let me give you some hints. As usual, we can set some notations. And for example, we can call Aij the entries of A, Bij the entries of B, then Cij the entries of the transpose of A times B, and finally Dij the entries of Bt times At. Of course, we can forget that by the properties of the transpose of a matrix, Cij is the same as Uji, where the entries Uij now describe the matrix A times B. Now, Cij, which we said is equal to Uji, is the row column product of the jth row of A and the ith column of B. Then it is given by Aj1, Aj2, and so on until Ajn times B1i, B2i, and so on until Bni, whose final result is the sum of the products of the form AJSBSI. We call this last result dagger, with the symbol dagger. Now, Dij is the row column product of the ith row of Bt and the jth column of At. But remember that the row of a transpose is the column of the original matrix up to a 90 degrees rotation. So we can rewrite the previous operation as B1i, B2i until Bni times Aj1, Aj2 until Ajn, whose final result is exactly the same dagger result that we found before. And this proves that nice property that we claimed before. And that's it for today. I'll see you in the next video. Thank you very much for watching. Please don't forget to like, comment, and subscribe. Thank you very much again. Bye.